In this video, we are going to discuss how to calculate magnetic field due to a long straight wire carrying current at a distance r perpendicular to the axis of the wire at points which are inside the wire and outside the wire. So here in this question, you have a long straight wire of radius r that carries a current I that is uniformly distributed over its cross section as shown below. Use Ampere's law to find an expression for the magnitude of magnetic field strength, first at a distance r from the central axis to the wire where r is less than capital R, and then at a distance r from the central axis where r is greater than capital R. So let's look at the first case here. In this situation, the value of r, which is the distance at which you are finding magnetic field, must be less than the radius of the wire. So let's take a point which is at a distance r from the axis of the wire, and we need to find what is magnetic field B because of the wire at this point. So to solve this problem, we are going to apply Ampere's circuital law. Ampere's circuital law says that integral B dot dl over an Amperian loop is equal to mu naught times the I enclosed by the loop. So in order to apply this law, let us first construct an Amperian loop that passes through this point. I construct a circular Amperian loop. And when I take integral B dot dl, I take this integral over the length of the loop. And we know for a circle, when you go around the circumference of the circle, integral dl will become equal to 2 pi r. So we write this as B times 2 pi r to be equal to mu naught times the I enclosed, where r is the radius of the Amperian loop, which is the same as the distance at which we are finding magnetic field, and I enclosed is the current enclosed within the loop. So let's rearrange this. We write B to be equal to mu naught I enclosed over 2 pi r. Now what is the current enclosed? The current enclosed in this region will not be the same as the original current I, which is the current through the entire loop, as we know that current is directly proportional to the cross-sectional area. Larger the cross-sectional area, more will be the current. Smaller the cross-sectional area, less will be the current passing through it. Now you can find current through this region by using the current density. We know that current density J is the total current per unit area of the wire. And I can find current enclosed within the loop, which is I enclosed, by multiplying current density with the area of the loop. So we get this as I area of the loop over area of the wire. So this will give me the total current passing through the Amperian loop. Now let's substitute this in our expression for B. We write B to be equal to mu naught over 2 pi r. In place of I enclosed, I write capital I area of the loop over area of the wire. Since the cross-sectional area of the wire is a circle, we can find this area by writing pi r squared. So let's substitute that for both. You get mu 0 over 2 pi r into I. Area of the loop will be pi into radius of the loop squared, which is small r squared. Area of the wire will be pi into radius of the wire squared, which is capital R squared. Now let's cancel off some quantity. We can cancel pi and pi here. We can cancel 1r from here and the square from here. And then we are left with P to be equal to mu naught I r over 2 pi capital R squared, where the small r is the perpendicular distance at which we are finding the magnetic field, and capital R over here is the radius of the wire. And if you look at this expression for magnetic field, you will notice that B over here is directly proportional to the distance from the wire. This means that magnetic field value increases as you go from the axis towards the radius of the wire. So if I were to plot a graph of B versus R, and let this be the radius, Magnetic field value as you go from 0 to capital R will increase as it is directly proportional to R. So this is how you can find magnetic field at any point inside the wire. Now let us discuss case 2, where we need to find magnetic field at a distance R such that R is greater than the radius of the wire. So let us first define this point R from the axis to a point outside the wire. Again, we are going to use Ampere's circuital law. Ampere's circuital law says that integral B dot dl is equal to mu naught times the I enclosed. And if I have to use this law, I have to create an Amperian loop. So let us create a circular Amperian loop of radius r around the wire. Now, when you take integral of magnetic field around this Amperian loop, you get integral B dot dl to be equal to B times 2 pi r, as integral dl for a circular loop is 2 pi r, equals mu naught times the I enclosed. So if I want to find magnetic field B, let's divide with 2 pi r. B becomes equal to mu naught I enclosed over 2 pi r. I enclosed is the current enclosed within the Amperian loop. In this case, it is the entire current flowing through the wire because the Amperian loop encloses the entire wire. So we can write B to be equal to mu naught I over 2 pi r. So this is the expression for calculating magnetic field at a distance r from the wire at points which are outside the wire. And we can also call this distance r as r perpendicular because this magnetic fields are at point which is perpendicular to the axis of the wire. Now if you notice this expression, you will see that B is inversely proportional to r. This means that at any point outside the wire, magnetic field value decreases as you go away from the wire. So if I were to plot a graph of magnetic field B and distance r at points which were outside the wire, that means after the radius r, the magnetic field value will decrease. Next, let's discuss part B of the question. A long straight wire of radius r carries a current I that is uniformly distributed over its cross section. Sketch a graph to represent magnitude of magnetic field strength B as a function of distance r from the axis of the wire. So in this question, we need to sketch a graph to represent magnitude of the field B as a function of distance r. So we're going to take distance r along the x-axis and magnetic field along the y-axis. Let this be the radius of the wire, which we will call as capital R. Points to the left are points which are inside the wire, and to the right are points which are outside the wire. Now in part A, we already discussed the expression for magnetic field due to a wire carrying current at different points. At points which were less than the radius r, which was inside the wire, this magnetic field was given as mu 0 I r perpendicular over 2 pi r squared, which means magnetic field was directly proportional to the distance r. In points which were outside the radius, you write B as mu 0 I over 2 pi r. That means B is inversely proportional to the distance r. So we need to sketch them accordingly. At points which are inside the wire, magnetic field value is increasing with distance. So going from 0 to radius r, the field value will increase in this manner. And then for points which are outside the wire, magnetic field value is inversely proportional to r. That means it will decrease as you go away from the wire, which you can show in this manner. So this is how you can sketch a graph of magnetic field with respect to the distance. Inside the wire, it will increase with distance. Outside the wire, it will decrease with distance.